So here we are, we're looking at impulse and momentum. And actually, as you go through, it- everything starts from Newton's second law of motion. Force is mass times acceleration. If we look at it, we can say that since acceleration is actually a change in velocity over time, you're speeding up or slowing down, and it's a rate, then you can substitute it, change in velocity over change in time. And if we want to move this over, right, multiply the change in time, you get something called fat mav. F delta t equals m delta v. It's the average force, and if it's a constant force, it's just the force, multiplied by how long the objects were in contact, and that says that is impulse, actually, and that's the same as the mass that's being accelerated, either sped up or slowed down, multiplied by the change in the velocity, or change in speed, if you will, if you don't care about direction again, that it experiences. And I'll show you a good example of this in a moment. So the idea is that impulse is the momentum change, and actually units of impulse are newtons times seconds, force and time. So it's actually the same. These units are exactly the same. So they can be used interchangeably. And looking at impulse, the symbol for impulse is J. It is force times the change in time, and you're going to experience the same change in momentum for any situation. If you might change the materials, as long as they have the same mass and the same speed, then you're going to experience that same change in momentum. So let me go through this. Let's say we have a small force, but it takes place over a larger period of time. So there is a car, and you get into a car wreck, unfortunately, but your airbag deploys, and it happens over a long period of time. This actually happened to me one time when a deer hit me, or I hit a deer. If that caught you, right? Newton's third law: the deer hit me just as much as I hit it. However, its smaller mass experienced a greater change in momentum. But anyway, the small force applied to my face, because of the greater change in time allowed by the airbag, I still had the same change in momentum because I was still going the same speed and had to bring that momentum down to zero. Now, if I did not have an airbag, then my face would take a short period of time to stop, to go from a high momentum to a low momentum, and I would experience a greater force. That would be an ouchie. That would hurt. So here's a graph of force versus time for, let's call it a tennis racket hitting a tennis ball. And you can see the force isn't constant, so I'm going to give you an average force. And actually, the area under this graph happens to be the change in momentum. It's force times time. And actually, the units even show you a Newton times a second. So the change in momentum, or the impulse for this, is about 12.6. It's not a bad idea to be able to identify that from a force versus time graph. So again, area under the graph, total impulse, 12.6 Newton times seconds, and the momentum change is the same. So if you know the impulse, you know the momentum change. If you know the momentum change, you know the impulse. They're exactly the same thing. So I'm giving the mass of 0.06 kilograms, that's the tennis ball's mass, and I want to know, excuse me, I want to know, based on the average force here, the change in momentum, what's going to be the change in speed for this ball? Well, again, there's the change in momentum. I know from my equations before, rearranging, that the change in velocity is going to be the change in momentum over the mass. I know the mass. I know the change in momentum, 12.6 Newton seconds divided by 0.06 kilograms. This ball is going to experience a 210 meters per second change. That's like about 450 miles per hour. Does that make sense? Well, barring air resistance, I'd say definitely, right? This object comes in at a negative velocity, a high negative velocity. It goes out at a high negative velocity. that change is very, very great. It's on one side of zero, and then it's really far on the other side of zero. So it's a very large change. I mean, that's why you can count tennis as exercise, right? It's not all the walking around. You have to apply a pretty decent force for this to work. And I don't think, well, okay. I will sing an impulsive world for you. Now, the person who made this was an incredible poetic genius, if I do say so myself, which I think I am the only one that says so. She's an impulsive girl in an impulsive world. Doesn't think first, just wants to be first. Takes so little time, her momentum slope does climb. Just so steeply, it rises quickly. She's an impulsive girl in an impulsive world. Does her work fast, bounces back fast. Her peak is at its prime. Just graph force versus time. People slower, their force average lower. She's an impulsive girl in an impulsive world. Okay, refer back to this graph if you want to understand the physics of that poem.